At this point, we've defined what error is when using the nth partial sum to approximate the sum of a converging series, and we've looked at some examples where we can find the error exactly. In this instance, I want to consider a series that converges and is also satisfying the conditions of the integral test. So I've written those up here. The sum converges, and we have an associated function f of x that's positive, decreasing, and I should say, and continuous on the interval from 1 to infinity. And in particular, this function f of x, if you plug in a whole number k, it evaluates to a sub k. These are exactly the setup we had for the integral test. And from a previous video, we've defined the error, e sub n, as the true sum minus the nth partial sum, which we can also express as what I've got boxed in green here as the sum from k equals n plus 1 to infinity of a sub k, meaning we get a sub n plus 1 plus a sub n plus 2, and so on. So we can't find the error exactly here because we've seen with the integral test, we can't assume that we can find the exact sum of the series. So the question is, how can we bound the e sub n, the error? We're going to go through what will look similar to the pictures we drew with the integral test. And in those pictures, we were trying to represent the sum from 1 to infinity by using rectangle areas. The only difference here is I'm trying to represent the sum from n plus 1 to infinity because of this green boxed definition here. So much like we did in that video, the goal is to identify the y values of this function at k equals n plus 1, etc. And so I started marking off on the y-axis exactly what those represent. And, oops, well, I should actually not quite right. That should be a sub n plus 1. So that's just coming from the definition of f of x. So what I want to do here is try to draw the sum from n plus 1 to infinity. So my very first rectangle, I want to have height a sub n plus 1. So I've found that height here. And I have a number of ways that I might choose to draw a rectangle that has that height and width 1. The reason, again, that I have that is that would mean the area of that rectangle would be equal to a sub n plus 1, the first term of my sum. So one way we can choose to do that is to just move out toward the right 1 unit. So this rectangle has area a sub n plus 1. And this rectangle would have area a sub n plus 2, and so on. And I can continue this process, and eventually the idea is I would have infinitely many rectangles, and the sum of the area of those rectangles is equal to what we're calling the error. So when I'm looking at this, to be clear, I'm thinking about these. Maybe I should be a little bit more precise. So in fact, it's this, all of these rectangles here. So I'm going to make this the same color that I've made my box around my error sum there. And my hope is that this makes it very specific what this picture is demonstrating. So it can be confusing that we're using the word error, and I think so far a lot of times when we talk about error in a picture like this, we're tempted to try to look at error and think about the jutting out part of the rectangles. But when I talk about error here, that's not what we're talking about. In particular, what we want to think of is that the e sub n in this case is the sum from n plus 1 to infinity of a sub k, and that equals exactly the green rectangles. That sum is represented by the area of those rectangles added together. So in this instance, if I'm trying to bound the sum of those green rectangles, well, we can see that we get a lower bound. The rectangles are larger than the area under the curve, and that is the integral of f, and we just need to make sure it's clear what our bounds are. The upper bound is infinity because, again, I've stopped short here, but the idea is this continues onward. The lower bound I want to choose so that the interval of the x values matches the interval over which my rectangles lie. And I can see that that leftmost x value should be n plus 1. So when I integrate from n plus 1 to infinity, I get a lower bound on my error. Just like we did with the integral test before, we can draw those same rectangles in a different way. So again, my approach is starting with that same part. But if I want to draw a rectangle with that height and width 1, last time I chose to kind of jut out to the right, well, we can do the same thing and move over 1 unit to the left. So again, this has area a sub n plus 1. And this has area a sub n plus 2. And I'm going to continue this process. Again, I'm going to kind of go until I run out of space here, but you should keep in mind that this is continuing forever, so that what starts at a sub n plus 1, we're actually going to get infinitely many rectangles off to the right. And what's important is, again, thinking about the green rectangles here. This is giving us the sum of these green rectangles is giving us the area under the sum of the areas of these rectangles is the error. Let's go back to this. So E sub n is still the sum from n plus 1 to infinity. And the idea here is that that is equal to the sum of the areas of the green rectangles. And I see that my green highlighter kind of bled out a little bit, but hopefully you are convinced that looking at this picture, these green rectangles sit beneath the function f of x. So this picture demonstrates actually an upper bound on the rectangles, so an upper bound on my error term. I can represent that upper bound, again, because it's an area under f of x, as an integral of f of x. This upper limit of integration is infinity, which demonstrates that these rectangles continue onward to the right. But to match up the x values with the interval over which my rectangles sit, the first x value here should be n. So we get together, so from the two pictures above, what we're getting in this instance is we've just found this upper bound, and the lower bound, if you recall, was from n plus 1 to infinity. So this is going to be important. What we're saying here is that anytime you're trying to bound error and the sum that converges is one in which you could use the integral test on it, then that means that you can use these error bounds. And of course, the upper and lower error bound here are very similar, and you just want to be very careful. The only distinction is that lower limit of integration. Now, I think it's sometimes people mistakenly switch these because we think of n plus 1 as bigger than n, but notice that this makes sense because there's more area between n and infinity than there would be between n plus 1 and infinity. Okay, so how do we use this? Let's look at an example. So here I've got the sum of 1 over k squared. If I had to say that converges, I would just reference that it's a p-series. However, keep in mind, I could go through the steps of using the integral test because f of x equals 1 over x squared is positive, continuous, and decreasing. And so that means this is eligible to use the integral test error bounds. A direct use of what we've just found above is a situation where here we're told that n is 10. I'm using the 10th partial sum. So we want to bound e sub 10 above and below. So e sub 10, we know that that should be bounded above by the integral from 10 to infinity of 1 over x squared dx, and below by the integral from 11 to infinity of 1 over x squared dx. Notice that I've got the same integral on either side, so just to save a little bit of work, I can find the integral from a to infinity of 1 over x squared, and then put in the appropriate value of a. So the antiderivative, whoops, sorry, that's not what I meant to write. The antiderivative, I'm going to treat this improper integral, b to infinity. The antiderivative would be negative 1 over x, where we're letting x here range from a to b, and we're taking that limit. And so here we're going to get that the limit is 0. When we plug in b, that's going to go to 0, minus a negative 1 over a. And so we just get 1 over a. Using that up here, that tells me I should get 1/10 as my upper bound and 1/11 as my lower bound. So if I were to add up the first 10 terms of this series, find that number, then we could use that to approximate the infinite sum. And what this tells us is that we would be within this range of values, within that kind of distance from the true sum there. So our approximation, maybe more importantly, is no more than 1/10 away from the true sum of the series. And if we're in a context where we know that that's good enough, then that would be a good situation. We might instead be curious to find out how many terms would we have to add so that we're close enough for what we'd like. And we can do this with the same kind of setup here. So I still have the same sum from 1 to infinity of 1 over k squared. If the question is here, how many terms would I have to add until I would be assured that my approximation was within 1 over 200 of the true answer? Well, let's think about what we have here. So we know that E sub n, in this case, is smaller than the integral from n to infinity of 1 over x squared dx. We know that. We need E sub n to be smaller than 1 over 200. Well, notice that it suffices here for us to find when the integral from n to infinity is smaller than 1 over 200. So thinking about if I can say that that integral is smaller than 1 over 200, well, we know E sub n is smaller than that integral, so that would automatically satisfy the desired inequality here. We don't have a similar idea with the lower bound, so we're really just focusing on the upper bound here. Now I'm going to point out, we've evaluated this above, so I can use my work for that, right? We didn't put n, we put a. So just looking at this part here, I'm going to use that result that this is true when the integral, which evaluates to 1 over n, is smaller than 1 over 200. Now that means that 200 is smaller than n. So with our example here, we have enough to be able to say that, that this would hold true as long as our value of n was at least 200. And the way that this works here, the error should get smaller as you use more and more terms in your approximation. So this inequality makes sense because the larger we make n, the smaller the error should be. And so we're really finding kind of a cutoff after which any n value greater would achieve this desired accuracy.